Hello everyone, and welcome to the Canadian Math Kangaroo contest. This video is on geometry and it's designed for grades 5 and 6. There are many things that you can do in order to do well on the Kangaroo contest. Practice solving questions from old contests is the best way to prepare. Today we will work through some problems from past contests. But before we do that, let's start by reviewing some basic geometric terminology, common two-dimensional shapes, and their associative formulas. The key to doing well on a geometric problem is understanding the vocabulary. So let's test your vocabulary with the following flashcards. On the count of 3, 2, 1, let's go. A straight path that goes without end in two directions. A line. Part of a line with two endpoints. A line segment. Part of a line that has one endpoint and goes in one direction without end. A ray. Describing lines that never meet. Parallel. Intersecting at right angle. Perpendicular. Two rays that share an endpoint. Angle. An angle that measures less than 90 degrees. Acute angle. An angle measuring 90 degrees. Right angle. An angle that measures more than 90 degrees and less than 180 degrees. Obtuse angle. An angle that measures 180 degrees. Straight angle. One of two angles whose sum is 90 degrees. Complementary angle. Two angles whose sum is 180 degrees. Supplementary angle. A polygon with three sides. Triangle. The point at which two line segments, lines, or rays meet to form an angle. Vertex. A triangle with all sides the same length. Equilateral triangle. Having the same size and shape. Congruent. Next to, side by side. Adjacent. A triangle with two equal sides. Isosceles triangle. A triangle with each angle less than 90 degrees. An acute triangle. A triangle that has one 90-degree angle. Right triangle. A triangle that has no congruent sides or congruent angles. Scalene triangle. A closed figure formed from line segments that meet only at their endpoints. Polygon. A polygon with sides all of equal length. Regular polygon. A polygon with sides that are two or more different lengths. Irregular polygon. A polygon with four sides. Quadrilateral. Two-dimensional shape with four sides and at least one pair of parallel sides. trapezoid. A trapezoid with two pairs of parallel sides and congruent opposite sides. Parallelogram. A parallelogram with all congruent sides and diagonals that intersect at right angles. Rhombus. A quadrilateral with four right angles. Rectangle. A quadrilateral with four equal sides and four right angles and has opposite sides that are parallel. A square. The property of having two halves that are mirror images. Symmetry. A line that divides a shape into congruent halves. Line of symmetry. A line joining opposite corners in a shape. Diagonal. Having the same value, worth, or meaning. Equivalent. A relation where the size of objects change in the same way. Proportion. The distance around a flat shape. Perimeter. The amount of surface inside a shape. Area. Next, let's look at some formulas. So here we want the perimeter of a rectangle and the formula for the area of a rectangle. The dimensions for a rectangle are simply identified as the length and the width. So for the perimeter of the rectangle, that's the distance around the rectangle, P is equal to length plus the width plus the length plus the width. For the area of the rectangle is equal to the length times the width. The perpendicular distance from the vertex to the opposite side of a plane figure. Height or altitude. Next, let's look at the formulas for calculating the perimeter and the area of a triangle. If the side lengths of our triangle are labeled as A, B, and C, then the perimeter of the triangle is A plus B plus C. For the area of the triangle, we need to calculate the height of the altitude of the triangle, and then the area is equal to base times height divided by 2. The Kangaroo contest is designed to have the easier questions first, and then progressively the questions become more challenging. So let's start by looking at a couple of questions from part B of some old competition papers, and then we'll progress to look at a more challenging problem. With question 1, we're told that the triangle and the square shown on the picture have the same perimeter. What is the perimeter of the whole figure? That of the pentagon. We are given some possible choices for answers. We're told A is 12 centimeters, B is 24, C 28 centimeters, D 32 centimeters, and E, it depends on the triangle measurements. So take a moment and think about the problem and then return for the solution. Welcome back. Let's now have a look at the solution to question 1. We were told that the triangle and the square shown in the picture have the same perimeter. What is the perimeter of the whole figure? So the first thing we're told is that the perimeter of the square equals the perimeter of the triangle. Our objective is to find the perimeter of the pentagon. Let's then start by calculating what is the perimeter of the square. On our figure, we're told that the length for one of the sides of the square is 4 centimeters. Because we're dealing with a square, we know that the length for all 4 sides are equal, they're congruent. So that means then that they must all be 4 centimeters. This allows us to work out then the perimeter of the square. So the perimeter of the square is equal to 4 plus 4 plus 4 plus 4, or in other words 4 times 4, which is 16 centimeters. That would be the distance around the square. Next, we want to work out what is the perimeter of the triangle. So the perimeter of the triangle would be the base times the length of the other 2 sides. Now we don't know the dimensions for the other 2 sides. So let's just label them. How about we label one A and we'll call the other length B. So we can then describe the perimeter of the triangle as 4 plus A plus B. Now we were told earlier that the perimeter of the triangle is equal to the perimeter of the square. We worked the perimeter for the square out to be 16. So that means then that the perimeter for our triangle is also equal to 16. We can then deduce that A plus B, the length of the sides A and B, must be equal to 12. So that 4 plus 12 is 16. Remember, the objective here is to find the perimeter of the figure, which is the outer shape. So it'd be the distance around the outside. We can now calculate that. So the perimeter of the pentagon, which is the 5-sided polygon, and this is an irregular shaped polygon, would be equal to 4 centimeters plus 4 centimeters plus 4 centimeters. Those are the 3 sides of the square. And then we have plus A plus B. So this is equal to 4 plus 4 plus 4. That's 12 plus A plus B. When we were looking at the parameter for the triangle, we were able to deduce that A plus B is 12. So we can make that substitution here, which means then that the parameter for the pentagon is 12 plus 12, which is 24. So the answer then to this problem is B, 24. Here's our next problem. Question 2. The tower on the picture is built from 3 shapes: square, rectangle, and an equilateral triangle. The perimeter of all 3 shapes is the same. The sides of the square is 9 centimeters. How long is the marked side of the rectangle? The options are A, 4 centimeters, B, 5 centimeters, C, 6 centimeters, D, 7 centimeters, and E, 8 centimeters. Take a moment to think about the problem and then join us again for the solution. Hi, welcome back. Let's have a look now at the solution. So we're told that the tower on the picture is built from 3 shapes: square, rectangle, and equilateral triangle. The perimeter of all 3 shapes is the same, and the side of the square is 9 centimeters. How long is the marked side of the rectangle? I'm going to start by redrawing the tower. And we're given that one of the sides of the square is 9 centimeters. This is 9 centimeters. Because we're dealing with a square, that means that all 4 sides of the square have a length of 9 centimeters. We can then work out the perimeter for the square. So the perimeter for our square then is 4 times 9, which is 36 centimeters. We're told that the perimeter for all 3 shapes, the square, rectangle, and equilateral triangle, are equal. Now, we're not given the dimensions for the rectangle, and we're not given the dimensions for our triangle, but we are given some valuable information. Our triangle is an equilateral triangle, and that means all 3 sides have the same length. They're all congruent. The perimeter for our triangle would be equal then to 3 times the length of each side. And that must be equal to the perimeter of the square, which is 36. That then means that the length of each side must be equal to 12 centimeters. So that 12 plus 12 plus 12 equals 36. I'm going to add that information then to our sketch. So the length then, oops, not 6, 12. So the length of each side then is 12. We can now focus on our rectangle. Our rectangle shares a side with our triangle. So that means then that the length of a rectangle is 12. That means this is also 12. And so then we're left to figure out what is the thickness of our rectangle. The perimeter of a rectangle would be equal to 12 plus 12, or 2 times 12, plus we've got the unknown thickness plus the unknown thickness, so 2 times question mark. The perimeter of the rectangle equals the perimeter of the square and the triangle, so it's also equal to 36. 2 times 12 is 24. If we take 24 away from 36, that leaves us with 12. That means 2 times our unknown thickness is equal to 12. So therefore, our unknown thickness is equal to 6 centimeters. So the answer then to this question is C, 6 centimeters. We can confirm this answer by now working out the perimeter of the 3 shapes and showing that they each equal 36. Let's have a look at another question. So here we have question 3. We're told that a quadrilateral labeled ABCD has sides. AB is 11, BC is 7, CD is 9, and DA is 3. And it has a right angle in A and C. What is the area of this quadrilateral? And we're given some options. So A is 30, B is 44, C is 48, D is 52, and E is 60. So take a few minutes and work through this problem, and then you can return for the solution. Welcome back. Let's have a look now at the solution. We're told that a quadrilateral ABCD has sides. AB is 11, BC is 7, CD is 9, DA is 3, and it has right angles in A and C. And the objective is to find the area of the quadrilateral. Let's add the dimensions, this information, to our diagram. So we're told that AB is 11 units, BC is 7, CD is 9, and DA is 3. We're also told that we have right angles at A, that's a right angle, and a right angle at C. The objective is to find the area. Now, because our quadrilateral is an irregular polygon, we want to break it up then into familiar shapes so that we can work out its area. Let's try to take advantage of these 2 right angles. If we were to cut our quadrilateral, cutting it through the diagonal that goes from D to B, we would then end up with 2 right angle triangles. We have a formula for calculating the area of a right angle triangle. It's base times height divided by 2. We can then work out the area for each right angle triangle and add them together to give us the area of the quadrilateral. So let's do that. So we have triangle DCB is a right angle triangle, and we'll work out its area, which is equal to 1/2 times the base. Let's make the base 9 and the height 7. So that gives us 63/2. The other triangle is triangle DAB, and its area is 1/2 its base, which is 11, times its height, which is 3. So that's 33/2. The area then of the quadrilateral ABCD is the area of the two right angle triangles. So 63 over 2 plus 33 over 2. We're adding together two fractions. They both have the same base, which is 2. So we'll add the numerators together over their common divisor. So we end up with 96 divided by 2, which gives us 48. So the answer then to this problem is C, 48. Let's now have a look at a more challenging problem. So question 4, we're told that ABCD is a square with side lengths of 10 centimeters. The distance from the point N to M is 6 centimeters. The non-shaded regions represent identical isosceles triangles or identical squares. Find the area of the shaded region inside the square ABCD. And you're given 5 possible options for the answer. So A, 42 centimeters squared, B, 46 centimeters squared, D, 48 centimeters squared, D, 52 centimeters squared, and last E, 58 centimeters squared. So take a few minutes and work through the problem and then return for the solution. Welcome back. Let's now have a look at the solution to question 4. We're told that ABCD is a square with side lengths of 10 centimeters. The distance from the point N to point M is 6 centimeters. The non-shaded regions represent identical isosceles triangles and identical squares, and we're asked to find the shaded region inside the square ABCD. So let's get started by labeling some of the dimensions that were provided onto our diagram. So we're told that ABCD is a square and it has side lengths of 10 centimeters. So that side is 10, this side is 10, they're all 10 because it's a square. Next, we're told that the distance from point N to point M is 6 centimeters. So from N to M is 6 centimeters. On the diagram, we see that we have congruent squares located in the 4 corners. If the distance from N to M is 6 centimeters, that means then that the distance from D to N and from M to C must be 2 centimeters. So that the total distance then along that side from D to C is still 10 centimeters. It's 2 plus 6 plus 2, which is 10. The objective here is to find the area of the shaded region inside the square ABCD. The area then of the shaded region because it's an irregular shape, it looks like an X with squares notched out of the corner. We can think of this shaded region as really the difference between the area of the square minus the non-shaded regions, where the non-shaded regions are the areas of the corner squares plus the 4 isosceles triangles. Now that we've kind of formulated our equation as to how we're going to calculate the area of the shaded region, our next step then will be to work out what is the area of the square ABCD, and then to calculate the area of the non-shaded regions and take the difference between them. So let's then start by finding the area of the square ABCD. So the side lengths of our square are 10 centimeters, and the area for a square is length times width, so it's 10 centimeters by 10 centimeters, or 100 centimeters squared. Next, we want to find the area of the non-shaded region. This area is made up of the area of the corner squares plus the area of the 4 isosceles triangles. For the area of the corner squares, we had worked out earlier the dimensions for the corner squares. They're 2 centimeters by 2 centimeters. So 2 times 2 then would give us the area for one of the corner squares, and we have 4 of them. So we have 4 times 2 times 2, which gives us 16 squared centimeters. Next, we want to calculate the area of the 4 isosceles triangles. So if we focus on one of the isosceles triangles, we know the base of the triangle is 6 centimeters. But we also know that these isosceles triangles are right-angled triangles. To calculate the area of a triangle, the formula is 1/2 times the base times the height. Now we don't know the base or the height of these triangles. Well, unless we take the base to be 6, but in which case we don't know the height or the altitude of the triangle. But there is a little trick we can do here. If you take the 4 isosceles triangles, because they're right-angle triangles, we can take them and shift them to form a square. So this is this triangle, and then we have the triangle up top, and the dimensions are 6 and 6. The triangle then to the left, right angle triangle, and then if we take the triangle then on the bottom, we end up then with a square which is 6 by 6, and the area then of this square is equivalent to the area of the 4 isosceles triangles added together. So the area here then would be 6 times 6, which is 36. The area then for the non-shaded region, which is the area of the 4 corner squares plus the area of the 4 isosceles triangles, is 16 plus 36, which is 52. The area of the shaded region was equal to the area of the square ABCD minus the area of the shaded region. So the area of the shaded region is then equal to 100, the area of the square, minus the area of the non-shaded region, which is 52, and we end up with a final result of 48 centimeters squared. So the answer then to this question is C, 48. This concludes our video, so I want to thank you for joining us. If you're interested in watching more videos, you can find them on our YouTube channel, and you can also visit Kangaroo Canada at mathkangaroo.ca. Okay, bye for now.